Yes, good morning, all of you. So, if someone can confirm that the screen is visible and I am audible.
Yes, sir.
Okay. So, we'll start in another minute from the point where we left. So, this is lecture 25, digital communication. So, yes, I think last time we were doing this. The concept of maximizing the SNR by correlating the signal with some template signal, and that template signal we said that should be the signal which is same, or in the terms of vectors it lies along the same direction as S, and its magnitude doesn't matter with respect to SNR. Why? Because we have seen that if we increase its magnitude, it will increase the signal as well as the noise proportionally. Okay, means same in the same manner. So with respect to the SNR or quantity of interest to us, this doesn't help us. Okay, so I think we left this derivation that after substituting, after substituting G as some function of S, or you can say scaled version of S, how do you get this? Okay, so we'll start from uh, the point where we left. Okay, okay. So first of all, let me state the theorem. So this is in continuation with what we were doing. So for linear processing, of a signal ST, corrupted by this in a better manner. Corrupted by white noise, the output SNR is maximized by correlating against ST. Okay, the resulting SNR is so SNR max. It means it says that there is no other possible signal with which you will correlate this signal ST to get a better SNR. Okay, it has to be with itself only. So twice of norm of S square divided by N naught. Okay, so we'll do one thing. I think I didn't do the derivation last time. Let me just complete it. Okay, so suppose let me do one thing. That is, we were at this point, we said that this is the SNR, or you can say this is what is the SNR is, and not by 2. Let me write it down. This was SNR max was nothing but this S comma G whole square divided by, let us see, and not by 2 into norm of G square, or EG. Okay, now suppose you substitute G as some alpha times S. Okay, or S of t, means G of t is nothing but alpha times S of t. So what do you get? Let us see it. So this is integration S into alpha times S d of t, which goes from minus infinity to infinity, and you have to take the whole square of it. This is the definition of this inner product. This inner product is defined like this. Divide by and not by 2. Okay. Now what is this G? G, this square is nothing but G times G, that is G square, so alpha square S square t d of t. Okay. So what it is, this is, let us say, numerator, if we talk about this, alpha square, integration minus infinity to infinity, s square dt's whole square. Okay. Now just remember that norm of g is under root of integral g square dt. Okay. So this is alpha square, this divided by n naught by 2 alpha square integral s square t dt. So we have not written t here. I think we should, or it's better if we keep t at some place so that you remember. So this is not, if this cancels out, one term cancels out, alpha square cancels out. So you are left with this divided by n naught by 2. And this is nothing but twice of n naught, 2 by n naught, norm of s square. Okay, so this derivation I didn't do last time. I thought that let me first state the theorem, then I would do this derivation. So it's simple to see, because if at all this loose end would be there, maybe some of you won't be able to derive finally. Okay. Now let us do one next part which is important, that is seeing, we need to see seeing correlation as a filtering operation. Okay, this is important. So how do you see that? Okay, because until now we have said that the operation which we would be doing is simply multiplying. This is what integration minus infinity to infinity. If I need to correlate it with some function, then I would be doing like this. This is the operation which I would do. But if at all you talk of filtering, then if at all you filter s of t through g of t, then you know this will be a number. Okay, this would be a number. That is a correlation value. But if you filter st through gt, it would be a signal output which is given by the correlation of the two. The tau and this goes on. And this is a function. Now the question is, can we obtain this number via putting some value of t? Okay. Question is, let us say this number is a. Can we obtain the number a by putting some value of t in yt? Okay, it means for a particular value of t in yt. By putting a particular value, I think the better word should be a particular value. T in yt. Okay, how do you do that? So this answer is yes, and this filter would be called as a matched filter. Okay, so that is a popular word which is called as a matched filter. So the answer to this is yes. Let us see how. Okay, so correlation with the waveform gt, correlation with the waveform g of t can be achieved using a filter h of t, which is equal to g star of minus t. Okay, and sampling at t equal to 0. Okay, let us see how. This would be interesting. Okay, let us say we have z of t as the filter's output, and this is given by convolution of I have used some different terminology, I think. Instead of st, okay, g star t is a number and y of t is this. Okay, gt can be achieved using a filter, and sample. What filter I used? Okay, JT, S of t, as this should be Y of t. Suppose let us be consistent with the notation, because otherwise the textbook consider this to be Z of t, but we have started with this, so let us assume it to be Y of t. Okay, Y of t would be nothing but S convolution with H. Okay, so that will be the output, because you are applying S of t to a filter H of t, and you will get an output Y of t. Okay, so this is nothing but this is equal to integral minus infinity to infinity S of tau into H of t minus tau d tau. Okay. Now suppose we sample it at 0. I want one value. This is a function. Suppose this is a function of time and this is a value. Okay. So let us say y of 0. So y of 0 is equal to minus infinity to infinity. Now you know that this is the claim, that if h of t is nothing but g star of minus t. So this is nothing but integration minus infinity to infinity S of tau into G star of tau d tau. Okay. So it means if at all my filter H of t is nothing but equal to G star of minus t, and if I sample the output at t equal to 0, if I take the value at t equal to 0, I will get this number, and this number is nothing but the correlation of S and G. Okay, this is a very, you will see a nice observation. Okay, so if at all we want to implement correlation with the help of filtering, so in this context, what can we say? We can say that we see that the SNR is maximized. We see that the SNR is maximized by choosing the filter, by choosing the filter impulse response, by choosing the filter impulse response as S star of minus t. Okay, why? Because this you can see from, refer to the theorem above. Refer to theorem. Let us give us a 9. Theorem should be 1. Let us keep it as 1. Okay. So we will refer to theorem 1 above. Okay. Now this is called how? See, we have seen that ठीक है, अगर हमें किसी से हमें आउटपुट निकालना है कोरिलेशन का, तो सिंपली हम अगर जैसे हमें S का G से निकालना है, तो हम इम्पल्स रिस्पॉन्स को G स्टार माइनस टी पुट कर देंगे. ओके, अब ये तो बात ठीक है, बट हम जानते हैं कि अगर हम कोरिलेट करना चाहते हैं, अगर हम सही में किसी सिग्नल को किसी से कोरिलेट कर रहे हैं, तो SNR कब मैक्सिमाइज होगा? जब उसी सिग्नल की कॉपी से कोरिलेट करेंगे, यानी S gets correlated with itself. So this G of t would be nothing but S of t. So G star minus t would be S star of minus t. Okay, so that is what is this. So now this is called the, the matched filter. This is called the matched filter for S. And we denote its impulse response, and we denote impulse response as the matched filter for S of t is denoted by SMFT, and this is nothing but S star of minus t. See why this derivation contains star, because the framework would be complex in general. Okay, but somewhere in order to make the explanation easier, or in order to understand or imbibe the concept in the first go, we consider the real framework. Okay, so this is S star of minus t. So another theorem, which is theorem 2. So these two theorems will form the basis of the receiver design. which we are basically will be doing soon, very soon. So for linear, so this is important because we are considering everything in the framework of linear processing. Otherwise, if linear processing नहीं होगी तो convolution define नहीं होगा, okay? Because convolution is for generally for LTI systems that output can be expressed in terms of this convolution thing, okay? For linear processing of a signal S of t corrupted by white noise, the output SNR is maximized. The output SNR is maximized by employing the match filter with impulse response SMF of t is equal to S star of minus t sampled at time t equal to 0. Okay. Now this is what the concept of match filter is. And you will observe that if at all we choose a pulse, suppose we are choosing a pulse like this to transmit our signal. Okay, this is the pulse, which is of width dB, that is the bit interval. This is t and this is your S of t, and you are doing some sort of an amplitude modulation, or let us say you are for +1 you are transmitting, sorry, for 1 you are transmitting st, and for 0 you are transmitting minus of st. Suppose this is the case. Then what will be the matched filter for this sort of transmission of st? The matched filter would be, so SMF of t would be equal to, what do? You basically do the flipping, okay, and this would be the matched filter. And the output of this convolution, let us convolve both of them, because that would be we doing. ST would be coming and it would be applied as an input to the filter with this impulse response S star minus t. So let us see what will be the output. So the output will be, if you convolve both of them, your output will be like this. I think if you remember the convolution of two Freck functions, so this will be the output. At 0, the value is maximum, and at minus t and t, this is 0. This is TB, and this is, okay. So that will be the output, and but the value you will take will be at t equal to 0. So you will take the value at t equal to 0. This is what you get. Okay. Now there is one important thing. Okay. That you will say that this impulse response SMFT is non-causal, and hence if it is non-causal, it is non-realizable. Okay, so in most of the textbooks you will find that there would be a time delay in SMF such that it becomes realizable. So let me write very important observation / design aspect. Okay. In order to make the match filter realizable, so that is, in order to make the match filter realizable / causal, we need to delay, we need to delay it by sufficient time. Okay. In the last example, in the example above, a delay of TB would do, and and the sampling time changes to t instead of 0. Okay, so this is what, let us see it, what we are saying. So if at all this was your s of t, okay, this was your s of t versus t, this is Tb. So what was your SMF? So SMF t was nothing but the flipped version, okay. This is Tb0 and this is, suppose any amplitude takes, now you delay. So if you need to delay to make it realizable, you delay it by Tb, okay. So this was nothing but SMF t minus Tb, okay. To delay it by, let me write it more clearly so that it is clear once you go back and read. Okay, so once you do that, I think it would, this would be minus Tb, sorry, I think I have not written it. Yes, this is minus. So this becomes like this. This is Tb, this is 0. Okay. Now you convolve both of them. Once you convolve both of them, what will be the output? So shifted version. So now convolve S of t, convolution with S of mf, which is t minus Tb. The output would be this sort of a waveform. This is now Tb. This is 0 and this is 2 Tb. Okay, so the sampling instant now would be Tb instead of being at 0. Okay. Yeah, it should be. Oh, yeah. Once you convolve, no? So this will be flipped, and when you start the convolution, so at the 0th point, the value will be 0 and it becomes maximum when it is Tb, and the output falls to 0 again at 2 Tb. Now, what is this expression? What is SMF of t minus Tb? When SMF t is nothing but S star of minus of t. So this is equal to, SMF t minus Tb is equal to S star of minus of t minus Tb. So this is nothing but S star of Tb minus t. So you will find this in most of the textbooks, okay. It will be delayed by some value. Now this delay is just to ensure that this filter is realizable. It should have a causal impulse response. It should not have a non-causal impulse response, okay. So this was important for us to know. In continuation, one more important thing, let us say, very important observation. This should be 1, and then we will go for 2. This is the second observation. Okay. So the second observation is, when the received signal is given by, when the received signal is given by S of t plus, sorry, S of t minus t naught, means it has a delay. N of t, the peak of the signal contribution to the match filter shifts to t is equal to t naught. It means you have to determine the sampling instant at which you will get the maximum power or maximum value as the output, and this should be when you are convolving it with a signal which has an equivalent delay, okay, to what we get input is, okay. So that's t is equal to t naught will be the point at which you will sample, which now becomes the optimum sampling time. Okay. So this is what the two important observations are. Now some properties of match filter, we will certainly close our section. Some properties of matched filter. What are those properties? Let us see it. So property A is optimum sampling time. This should be known. See, if you remember this, that there won't be any problem with you identifying the optimum sampling point. Okay, so optimum sampling time is determined by the peak of the signal contribution to the match filter output. Okay, this we have seen that जो optimum sampling time होगा वो noise पे dependent नहीं है, वो peak of the signal contribution to the match filter output पे dependent है. Okay, pretty much the reason for this is, let us see, statistics of noise contribution. Now, why do we call statistics of noise contribution? Why? Because we have modeled things in this way. We say that noise is only the random phenomenon. S of t is a completely deterministic thing. Okay, so once we say that noise is a random phenomena, so whenever you will take its convolution or you will do some sort of filtering on it, it will lead to a random variable. Okay, so that random variable will define some random SNR. So we don't want that. What do? We take the instantaneous power of the signal and divide it by the expected power of the output. Okay, that is the variance से आप divide कर देंगे उस random variable, because this will give you one possible number. Okay, otherwise for several different, you can say, sample functions, you will get different SNRs. Okay, so then there is no way you can define a fixed thing, because you need to have a receiver. It cannot be random. It needs to do some fixed operation. Okay. So statistics of noise contribution to the matched filter output, do not depend on the sampling time. Because WSS noise into an LTI system yields a WSS process. Let me just close it on the next page. Next slide. Now, what does it mean? It means that if at all white and stationary noise is the assumption, if we are keeping it into, or if we are feeding it to an LTI system, why? Because we are either doing match filtering or some sort of a correlation. Basically, we are doing match filtering. So in the case of match filtering, the output, because it's an LTI system, output would also be a white and stationary process. Now, the requirement for white and stationary process is that the variance and mean both are not functions of time. Okay, so it means it remains fixed. You sample it at any point, or the random variable which I will obtain by sampling at any time, the variance of that would be fixed. Okay. So this should be known because we basically mean and variance are not functions of time. Okay, this is important. Now the intuitive thing. Intuitive thing means that what really we do in match filter. So intuitive reasoning behind match filtering. So this is important to understand that what intuitively what really we are doing. Okay. So match filter enables us to implement an infinite bank of correlators, each corresponding to a version of our signal template at a different delay. This can be clearly seen from what we are doing. Okay. Let us see from this, because what do we do is we convolve S of t with its own, let us say a copy with shift. Okay, this is nothing but we will do integration minus infinity to infinity S of tau into S star of t minus tau d tau. Okay, so this is nothing but your output y of t. Okay, so what happens? Let us see. So y of t infinity is star of tau minus of t minus t tau. Okay, now your tau variable is here. So this is what basically you are doing the correlation of the signal with itself, but and the second copy is delayed by a different values of t always. मतलब अगर आप t की कोई भी पर्टिकुलर वैल्यू लेंगे तो आपने क्या किया है, आपने s को थोड़ा सा डिले किया आपने t माइनस कैपिटल T से और उसका अपने साथ ही कोरिलेशन कर दिया. That is what this match filter enables us to implement an infinite bank of correlates. Why? Because here t can take any possible value on the real axis. Okay, so this t implicitly takes infinite number of values. So it means we are implemented an infinite bank of correlators. Why? Because if I just substitute any value of t, I will get a number that is nothing but a correlation of signal with itself, and but with a different delay. Okay, each corresponding to a version of our signal template at a different delay. So this is intuitively what we have done. If that is the case, then we choose that value of t which maximizes this power. Okay, and that is we have already seen. For the case when capital T we choose at 0, the optimum sampling time would be 0. And for other cases, you have to see what will be the sampling. Most probably it would be capital T if at all ST is time limited. Okay. So you have to do some examples in order to get a feel of it. Now we will shift, we will come to the next part, which is now let us study how does the AWGN process, additive white Gaussian noise process, creates trouble for us. Okay, so we will study now error rate due to noise. This is important section. So implicitly we have from now on or from today and from this moment onwards, we have started studying the, we will say, receiver defined. Okay, so first very basic receiver we would be studying. That is error rate due to noise. Okay, let us go ahead. Is there any comment? No. So in this we would use the statistics learned to date. So we know that, yeah, yeah, just hold. Yeah, sorry for the interruption. So we know that the match filter, we know that the match filter is the optimum detector of a known pulse in AWG, additive white noise. Okay, this I should write. This is additive white noise. Okay, hence we can now study the error rate due to noise in a binary PCM system. So let us now return to the case of the first system which we studied, that was a binary PCM system. Because up to now we have designed systems and we have also studied the phenomenon which will basically create trouble for us, but we have not yet combined both of them and studied. Okay, so we will be now combining the systems. It means आप एक binary PCM system का transmission study करेंगे जिसके अंदर वो एडिटिव नॉइज से इम्पैक्ट होगा या इफेक्ट होगा। तो एरर कैसे आएगा सिस्टम में वो हम स्टडी करेंगे और कितना आएगा ये जानना बहुत जरूरी है। और वो सब डिपेंड करेगा कि नॉइज की वेरिएंस क्या है, सिग्नल का पावर क्या है, तो हम वो देखेंगे कैसे होगा। Okay, so we have not yet told that this noise is Gaussian. We would be considering mostly Gaussian noise, but in general it would be an additive white noise. Okay, maybe we only need this to study this error rate. Let us see. Okay, so consider a binary PCM system. Consider a binary PCM system based on polar NRZ, based on polar NRZ signaling. So you know that if at all you are studying a PCM system, that would be mostly at baseband. So at baseband, what pulse shape you use or what scheme you use, you need to specify. So what is polar NRZ? So in polar NRZ, your 1 is transmitted by like this, that it would be taking an amplitude value of A, and this would be a TB. This I should put it at this point better. Okay, and 0 would be with the negative pulse. Okay, this was a minus of A. Okay, so 1 is represented by this, then 0 is represented by this, and you will get some sort of a waveform like this. Generally this is like this. You must, I think we have gone through it when we were studying for midsem. Okay, so this is the ultimate baseband waveform you will get. Now this baseband waveform goes through a AWG channel or AWN channel right now we have said. So what happens? So it goes through a channel which adds white noise, of zero mean and power spectral density of n naught by। ओके, अब ये ऐड हो रही है इसके अंदर। अब आप देखेंगे कि अब कैसे डिजाइन करें सिस्टम को, रिसीवर कैसे डिजाइन करें। दैट वुड बी अ the task basically. Okay, so let us see. So in the signal, let us consider a signaling interval of TB. जैसे कि एक आप पल्स मान लीजिए, जैसे कि एक ये पल्स जा रही है. For example, let us say this is your pulse. So this is what? This is your 1, this is your 0, this is your 1, 1, and this is your 0, 0. And this is your, you can say, signaling intervals. And this signaling interval is of width TB. That must be known. So ये TB है, ये भी TB है, ये भी TB है. सो कंसिडर, तो अब हम एक सिग्नलिंग इंटरवल को लेते हैं. पहले हम देखेंगे कि एक टीबी विड्थ के इंटरवल में हम 0 और 1 को कैसे डिटरमाइन करेंगे. 0 था या 1 था. अब आप कहेंगे एम्पलीट्यूड बदल जाएगा, क्योंकि अब ये रैंडम वेरिएबल ऐड करेंगे. अभी तक इसका एम्पलीट्यूड प्लस ए और माइनस ए था. अब सपोज मैंने AWGN इसमें ऐड हो गया, तो वाइट गॉसियन नॉइज तो आपको पता है कुछ भी वैल्यू ले सकती है, मतलब सम सॉर्ट ऑफ अ गॉसियन रैंडम, और सॉरी, इट्स अ वाइट नॉइज, इट कैन टेक एनी वैल्यू. So whatever value it takes, it will change the amplitude of what you receive. Now from that changed amplitude, how will you say that you received 0? The transmitted bit was 0 or 1. So this is a big problem. Okay, so let us design this. So in the signaling interval, in the signaling interval 0 to t, interval 0 to tb. So let us take a signaling interval. Received signal is thus written as x of t is equal to plus a plus wt, okay, or minus a plus wt. Let us remove this plus, otherwise this would create confusion. So सिग्नलिंग इंटरवल में दो ही पॉसिबल वेवफॉर्म्स आपको रिसीव कर सकते हैं आप. अगर ये कब रिसीव करेंगे? इफ सिंबल 1 was transmitted, and this when symbol 0 was transmitted. Okay, here TB is the bit duration, and A is the transmitted pulse amplitude. So अब ये दो पॉसिबिलिटी हैं जो आप, मतलब xt क्या है? xt या तो a प्लस wt होगा या माइनस a प्लस wt होगा. अभी आपको यही बताना है कि xt क्या था. मतलब xt में से आपको 0 से tb के बीच में xt की वैल्यूज हैं आपके पास. अब आपको उन सारी वैल्यूज को यूज करके ये डिटरमाइन करना है कि 0 ट्रांसमिट हुआ है कि 1 ट्रांसमिट हुआ है. बस ये काम हमारा. ओके, फर्स्ट assumption is the transmission takes place. So ये सिर्फ और सिर्फ एडिटिव वाइड नॉइस चैनल है. मतलब हमने ये नहीं माना है कि सिस्टम के अंदर कोई बैंड लिमिटेड फैक्टर है, क्योंकि अगर हम मानेंगे कि चैनल बैंड लिमिटेड है तो हमें नाइक्विस्ट क्राइटेरिया फॉर ISI अवॉइडेंस को भी रोल में लेना पड़ेगा. इसमें ये सिंपल वाली पल्सेस से फिर काम नहीं चलेगा, बिकॉज रेक्टेंगुलर पल्सेस वुड अल्टीमेटली लीड टू ISI at the receiver. So we need to then design pulses which would basically take into role the band limited nature of the channel. So पहली assumption ये है कि अभी चैनल इनफाइनाइट बैंडविड्थ का है, मींस ट्रांसमिशन टेक्स प्लेस over an infinite bandwidth channel. Okay, that is channel is not band limited, so no ISI arises. इसका मीनिंग क्या है? इसका मीनिंग ये है कि जो बिट ड्यूरेशन में 0 से TB के बीच में सिर्फ एडिटिव वाइट गॉसियन नॉइज हमारे सिग्नल को खराब कर रही है. एडिटिव वाइट नॉइज हमारा ISI खराब नहीं कर रहा है. तभी हम सिर्फ और सिर्फ ऐसा रिसीवर डिजाइन करेंगे जो इन्हीं दो पॉसिबल वेवफॉर्म में से एक को चूज करेगा, मींस ए या माइनस. अगर ये ISI भी होता तो उसमें फिर ISI को भी रोल में लेना पड़ता है एज अ डिस्टॉर्शन कंपोनेंट. Okay. One assumption, first of the assumption is this. A second assumption, which is also important, that receiver यू कैन से कि भाई रिसीवर को एक रैंडम वेव फॉर्म आ रही है एक्सट्रीम, तो रैंडम बन गई है, वो ट्रांसमिट तो उसने ये वाली वेव फॉर्म करी थी, बट नॉइज ऐड होने के बाद वो कुछ भी ऐसे भी हो सकती है. लेट अस से दिस इज व्हाट इट इज रिसीविंग, मे बी समवॉट लाइक दिस. सो इन दिस वेव फॉर्म हाउ डज इट नो वेयर यू हैव टू सैंपल, कि टीबी मतलब 0 से टीबी की जो बिट ड्यूरेशन है वो कैसे उसको पता चलती है, ये भी तो पता होना जरूरी है कि 0 से टीबी हम किस सेगमेंट को बोलेंगे. इस वेव फॉर्म में तो इट्स क्वाइट क्लियर, यू कैन इवन सी इट विद द नेकेड आई दैट इसमें टीबी ड्यूरेशन कौन सी होगी. Unless there is a long sequence of ones and zeros, you can easily say what will be the TB. So receiver has acquired. So second assumption is receiver has acquired knowledge of the. So this is important to write. कि हम क्या मान रहे हैं, रिसीवर को क्या क्या पता है. बेसिकली दिस इज द वे कम्युनिकेशन सिस्टम्स आर स्टडीड. मीनिंग क्या है इस बात का, कम्युनिकेशन सिस्टम्स के बहुत सारे कंपोनेंट्स होते हैं. तो एक होता है एस्टिमेशन कंपोनेंट, कि आप एस्टिमेट करते हैं कि सैम्पलिंग टाइम कहाँ कौन सा होगा या किस पॉइंट पे टीबी का इंटरवल हो गया, उसके लिए एक सेपरेट मैकेनिज्म है. सो राइट नाउ हम मान के चलते हैं कि उस मैकेनिज्म ने हमें जो रिजल्ट दिया है वो करेक्ट दिया है. मींस हमें जो सैम्पलिंग टाइम बताया गया है या बिट ड्यूरेशन बताया गया, सॉरी इट शुड नॉट बी सैम्पलिंग टाइम, इट शुड बी बिट ड्यूरेशन. सो जो बिट ड्यूरेशन के पॉइंट्स बताए गए हैं, जैसे ये वाले पॉइंट्स, फॉर एग्जांपल these dotted lines, they are correct, these dotted lines. Okay, so they are correct. So receiver has acquired knowledge of the starting and ending times of each transmitted pulse. Basically, I should not write basically, it should be also, obviously. Also, pulse shape is known. Pulse shape is known, but not the polarity. ओके, सो ये वाला फैक्टर है. आपको पल्स शेप तो पता है बट पोलैरिटी नहीं पता है. ये बहुत आसान है क्योंकि आप जो यूज कर रहे हैं, लेट अस से यू आर यूजिंग पोलर एनआरजेड एंड दिस इज अ बाइनरी पीसीएम सिस्टम, दिस योर रिसीवर मस्ट आल्सो बी नोइंग. सी अब आपको पता है कि if you are talking over mobile, okay, so mobiles have some sort of a settlement in between सेंडर और रिसीवर के बीच में, कि क्या पॉसिबल सेंड हो सकता है और क्या पॉसिबल रिसीव हो सकता है. उसके ऊपर इंफॉर्मेशन ही सिर्फ रैंडम हो सकती है, मैकेनिज्म रैंडम नहीं हो सकता. इट मींस द वे यू ट्रांसमिट, द वे यू रिसीव, or if at all you are modulating over something, suppose let us say I am modulating over a RF carrier of 900 megahertz, so this will be known at the receiver. Otherwise, where will it filter? It means you need to put up a band pass filter around 900 megahertz, that is known at the receiver. So receiver will be knowing that you are using this, you are basically a binary PCM system is transmitting with polar NRZ signal. So this it knows. So polar NRZ signaling में आपको सिर्फ एक पल्स शेप अगर पता है कि ये वाली पल्स शेप है कि 0 से टीबी के बीच में ए है, तो दूसरी आपको पता है माइनस ए हो जाएगी, बस पोलैरिटी नहीं पता है आपको, क्योंकि आपको डेटा सीक्वेंस नहीं पता क्या डेटा इनपुट में आया बाइनरी पीसीएम सिस्टम के 101011 और 000011, व्हाट दिस बिट सीक्वेंस इज कमिंग, दिस इज नॉट नोन. सो इम्प्लिसिटली दिस मींस पल्स शेप तो आपको पता है कि क्या ट्रांसमिट हो रही है, बट पोलैरिटी नहीं पता. सो अब आपको बेसिकली एक्सटी में से 0 से टीबी के ऊपर पोलैरिटी निकालनी है कि ए आया है या माइनस ए आ रहा है. अभी वेव फॉर्म तो बिल्कुल रैंडम हो चुकी है, मतलब डिस्टर्ब हो चुकी है वेव फॉर्म पूरी. तो अब वो देखते हैं हम कैसे करते हैं. ओके, सो द सॉल्यूशन इज, so let us say you are given the noisy signal x of t, the receiver is required to make a decision in each signaling interval Okay, whatever I have said, I am just writing it down first. As to whether, the transmitted symbol is a 1 or 0. Okay. So what will be the typical receiver is, let us say, or the system diagram is your S of t over a bit interval. So you can say we are considering it over a bit interval, or even if more generally you can consider it. So this is what the channel does. It will add a white Gaussian noise, which is, so right now we have specified that it is having Gaussian nature as well. Initially we said that it is an additive white noise, but it can, now we are assuming it to be white Gaussian, or from start itself we should say this, so we can remove this confusion. We should use GN only, otherwise okay, let us take it to be Gaussian. So it's at this. Now, what you will do? You know that if at all your signal is of the form yt is equal to s of t plus n of t, or you right now in our case you will w of t, then in order to maximize the SNR, you need to use a matched filter. Okay, so matched filter to s of t. So you will use a matched filter here. Note that this match filter will now work over the bit duration, okay, 0 to TB. And let us say, because we know that if there is an output from the match filter, you need to sample it. Let us say you sample at t equal to TB. And then this is the decision device. Okay, so this decision device has to basically tell you whether 1 is transmitted or 0 is transmitted. Okay, it has to give you a choice. Now let us denote see ये जो सारा सिस्टम हम स्टडी कर रहे हैं ओवर दिस बिट इंटरवल स्टडी कर रहे हैं ओके सो ओवर दिस बिट इंटरवल यू विल से s of t would be nothing but means s of t can this is the pulse shape okay s of t is the pulse shape it is plus a the magnitude is plus a and it's of length tb and either it would be means minus a would be the polarity once your zero is transmitted okay बट जो मेन कंपोनेंट है वो एस ऑफ टी है सिर्फ यहाँ पे प्लस ए या माइनस ए आएगा अगर आप एस ऑफ टी को 0 से टीपी के लेकर एम्पलीट्यूड 1 मान के चलते हैं तो मैच फिल्टर आपको सिर्फ एस ऑफ टी से लगाना है उससे क्या है कि मैच फिल्टर में जो भी आप स्केलिंग कर रहे हैं उससे कोई फायदा मतलब फर्क नहीं पड़ेगा लेट अस सी फर्स्ट लेट अस डू इट एंड आई विल थ्रो सम लाइट इन द नेक्स्ट क्लास सो लेट y denote because let us first do the concept and then we will deep deeper let y denote the sample value y denote the sample value obtained at the end of a signaling interval okay so this is let us say after this is let us say this is y okay instead I should rub this because this will lead to confusion okay. अब y के बेसिस पे y एक नंबर है अब नंबर देख के आपको बताना है कि 1 या 0 है सो अब आप कोई ना कोई थ्रेशोल्ड चूज करेंगे कि अगर इस थ्रेशोल्ड से बड़ा है तो आपका 1 होगा और अगर थ्रेशोल्ड से छोटा है तो वो 0 होगा ओके let me just write that fact down first of all yes then the logic is, so y greater than less than, you can say some lambda threshold. So if it is greater than, you will take 1 as a call, and if it is less than, you will take 0 as a call. This is a threshold. ओके बिकॉज अब एक नंबर आया है, उस नंबर को बेसिस पे आपको फैसला लेना है 1 या 0. तो आप यही करेंगे कि भाई ठीक है, एक वैल्यू फिक्स कर लेंगे कि अगर इस वैल्यू से बड़ा आया तो मैं 1 के फेवर में फैसला लूंगा, और छोटा आया तो 0 के फेवर में. अभी इस लैम्डा की कैलकुलेशन भी हम कर सकते हैं, विल डू इट टुवर्ड्स द एंड, दैट हाउ डू यू चूज दिस लैम्डा. ओके, अनदर पॉसिबिलिटी इज y इक्वल टू, तीन ही पॉसिबिलिटी है, तो लैम्डा से बड़ा होगा या लैम्डा से छोटा होगा या बराबर होगा. बराबर होगा अगर, तो रिसीवर just guesses between 0 and 1. Okay, such a decision is same as that obtained by tipping a fair coin. Now what it means, ठीक है, अगर लैम्डा से स्ट्रिक्टली बड़ा है तो हमने कहा 1 होगा, लैम्डा से स्ट्रिक्टली छोटा है तो हमने कहा 0 होगा. पर अगर बाई चांस लैम्डा के बराबर हो जाता है, तो अब इसका मतलब ये है कि जो आपका डिसीजन स्टैटिस्टिक या डिसीजन वैल्यू आई, यानी y आया, अब आपकी चॉइस है, आप या तो 1 भी चूज कर सकते हैं या 0 भी चूज कर सकते हैं. मतलब ये आपको डिलेमा आता है. अब इस डिलेमा में चाहे आप 1 चूज कर लें चाहे आप 0 चूज कर लें, कोई फर्क नहीं पड़ने वाला है. क्यों? क्योंकि आप सही में whatever you have obtained has given you no way to decide. Okay, so that can be easily done by randomly choosing between 1 and 0. मतलब हाफ प्रोबेबिलिटी से आप 1 चूज कर सकते हैं, हाफ से आप 0 चूज कर सकते हैं. दिस कैन बी डन बाय flipping a fair coin. Okay, now in such systems, what types of error can occur? Okay, so with this as the basically our system, what types of error can occur? 0 is transmitted but you choose 1. Okay, and 1 is transmitted means if the transmitter is transmitting 1 but you choose 0. So these are the two possible errors which can happen. Okay, so I think we would start the error calculation in the next class. Up to this point, I feel that we can close our class for today, because I want to start and finish up the error calculation in a go. It is only a task of I think 20 minutes. Okay, so we will do it in our next class. Anyways, this Friday is a holiday, so what to do? But I will inform you whatever I think. Okay, so we are done for today. Those who want to stay back to discuss something, they can, others can.